So in today's video, we're going to continue to talk about inverse trigonometry, and specifically we're going to see how inverse trig can work with within a right triangle. But before we get into that, I just wanted to do one more example along the lines of what we were doing yesterday. So I'll give this to you as a warm-up problem. So we did an example that was similar to this at the end of the video from yesterday, and then I also put a problem like this on the worksheet. So if you watched the video and did the worksheet, there's a good chance you'll know how to do this, but yeah, so feel free to pause the video and try this yourself, and then we'll go over it together. So you're evaluating tangent of inverse cosine of -2/3. So remember, you want to start on the inside and kind of work your way out. Okay, so how do we do this? Well, this is a little bit different from some of the other ones that we were doing in yesterday's video, because inverse cosine of -2/3 is not one of the angles we're familiar with, right? It's not going to be like pi/6 or pi/3 or something like that. So instead, like we were actually not going to find the angle inverse, inverse cosine of -2/3 is an angle, right? Whenever you're doing inverse trig, you're coming up with an angle. So it is an angle, but we're not going to actually find that angle. We're just going to kind of draw a picture that will help us understand that we don't really need to know the angle, but we can kind of find all the information we need in order to evaluate tangent. So this stuff here, inverse cosine of -2/3, is equal to some angle theta, where theta is an angle in the interval from 0 to pi, right? Because that's where inverse cosine, where the kind of answers come from. So it's an angle in the interval from 0 to pi, basically with a terminal point that has -2/3 as its x-coordinate. We don't really care, or we will care, but right now we're not talking really about the y-coordinate. We just know that the x-coordinate is -2/3, right? Because that's what cosine corresponds to. So let's just draw a picture here. It's not super important that it's a great picture, but I think it does help to have some kind of a visual. So if the y-coordinate, or sorry, the x-coordinate is supposed to be -2/3, just to kind of get a visual of where that is, well, here is -1, right? And here is 0. And so -2/3 is going to be like maybe -1/3 here, -2/3 is somewhere like there. So that means that we're going to a point on the unit circle. So we want to go up to the unit circle, and the x-coordinate should be approximately -2/3. And maybe I'll use another color for y, because that's going to be kind of our next step. So here's our angle theta. Okay, so now what do we want to figure out? We want to find tangent of that angle. And so how are we going to find tangent of that angle? Well, tangent is going to be equal to the y-coordinate over the x-coordinate. And in order to find that, we need to figure out what the y-coordinate is, right? So we want to find that y-coordinate. So we know that any point that is on the unit circle is going to satisfy x² plus y² is equal to 1. So we can do -2/3 squared plus y² is equal to 1, and basically just solve this for y. So we're going to get 4/9 plus y² is equal to, and then 1 can be written as 9/9. And then we can subtract 4/9 from both sides, and so we're going to get y² is equal to 5/9. So 9/9 minus 4/9 gives us 5/9. Then we can take the square root of both sides. So we're going to get y is equal to plus or minus square root of 5/9, which can also be written as plus or minus square root of 5/3, right? Because square root of 9 is 3, square root of 5 can't be simplified, so we can just leave it as square root of 5. So how do we know whether it's plus or minus? Well, going back to our picture here, we can see that the y-coordinate is positive, right? Because of where we are in the unit circle. And that basically comes from the fact that inverse cosine has to be angles in this part of the unit circle. So that means that the y-coordinate is guaranteed to be positive we know that our original angle was not this one down here, right? That would also be an angle that has an x-coordinate of -2/3, but because we found this angle using inverse cosine, we know for sure that it's in the top part of the unit circle. And so this tells us that, that it's positive. And so this is because theta is in the interval from 0 to pi. Okay, so now we know our x-coordinate and our y-coordinate, and now we can figure out what tangent is. So we want to do tangent of our angle theta, where theta is the angle we found in the first part. And so what is tangent of theta going to be? It's going to be that y-coordinate we just found, which was square root of 5 over 3. And then we're going to divide that by our x-coordinate, which we know is -2/3. And so this is going to simplify to square root of 5 over -2. And kind of a more conventional way of writing that would be -√5 over 2, just moving that negative sign out from the fraction. And that's it. And with tangent, I think it's always nice to kind of, as like a rough check for your answer, just look at the picture and make sure it makes sense that it's negative or positive. So in this case, you're always looking at the slope of that line, as that's what tangent is basically. So looking at the slant of this line, we can tell that it's negative slope. And so it makes sense that tangent was negative. Okay, so we are now going to get into right triangles again. So as I mentioned earlier, we kind of bounce back and forth between chapter 5 and chapter 6. So chapter 5 and chapter 6 are basically designed so that in the book you're kind of it tells people, teachers or students, that you can do whichever chapter first that you want. They basically follow like the same topics, but just through two different viewpoints. One viewpoint being the unit circle and the other viewpoint being triangles. And so I personally like to kind of go back and forth. And so as we do each topic, kind of see how does this play out in the unit circle? How does it play out in right triangles? So that's why we are back in chapter 6. And specifically it's section 6.4. And we're going to look at inverse trigonometry, in right triangles. So I want to start by reminding you what we were doing with right triangles kind of earlier on in the quarter. So we're not really getting into inverse trig just yet. But so remember from earlier in the quarter, I forget when exactly we did this, like pretty early, maybe even the first week, so remember from earlier, if you know the angles, so maybe I'll underline that. If you know the angles of a right triangle, you can use trigonometry, or I'll say trigonometric, to find the sides. So just to give a brief example, like let's say that you have a right triangle. And I always try to use this like ink to shape tool, and sometimes it lets me down. Sometimes I feel like it would be better if I just did it myself. No, it's a little crooked, but that's okay. So let's say that we know that this angle is 40 degrees, and we know that this side is 5, and this is the side we're trying to find. So problems that we were doing earlier in the quarter were kind of along the lines of, okay, so we know the angle, we're trying to find the side, therefore we can do something like this. We can say sine of 40 is equal to 5 over x. And so that tells us that x times sine of 40 is equal to 5. And so that tells us that x is equal to 5 divided by sine of 40, which is approximately equal to 7.78. So that's the kind of stuff we were doing earlier in the quarter. I guess I should make that a right angle. So now we're going to be kind of doing the opposite type of situation. So again, in that example, we knew the angle, and we could have found this other angle, right, using just the fact that the three angles add up to 180. And then we could also find, we didn't try to find this side, but we could have found this side if we wanted to. But now we're going to be dealing with kind of an opposite situation where we know the sides of a triangle, but we don't know the angles. So in this section, we will see that if you know the sides of a right triangle, you can find the angles using, so what would you think? Well, now we're not going to use regular trigonometry, we're going to use inverse trigonometric functions. So for example, let's say that we had a triangle. I'll give this thing another try. So let's say we have a right triangle, and we know that we know two of the sides. Let's say we know that this side has a length of 6 and this side has a length of 9. And let's say we're trying to find this angle. So instead of using regular trigonometry, we're going to end up using inverse trigonometry. And basically, you can kind of set it up by starting to write something down in terms of regular trig. So how would we relate the information we have here? So we have an angle theta, and we have two side lengths, 6 and 9. And so going back to right triangles, remember that we had this kind of language where we said the adjacent side, the opposite side, the hypotenuse. In this case, we know the adjacent side and we know the hypotenuse. And so that corresponds to cosine, right? Cosine is the function that relates an angle together with the adjacent and the hypotenuse sides. And so we can say cosine of theta is equal to 6 over 9, which reduces to 2 over 3. And so what does that mean about how to find theta? Well, because cosine and inverse cosine kind of work backwards from each other, that tells us that theta is going to be equal to inverse cosine of 2/3. And so if you type this into a calculator, you'll find that that's approximately 48.19 degrees. So by the way, in this section, for the most part, we'll be working in degrees just because they're a little bit more kind of relatable for these kind of real world situations versus on the unit circle where we're usually looking at things that are more kind of like perfect multiples of certain angles. So why did this work the way it does? Well, because remember, regular cosine, you plug in an angle and out comes a number. And inverse cosine, you plug in a number and the answer is an angle. And so it makes sense that if the stuff that we're working with are like side lengths of a triangle and we're trying to find an angle, it makes sense that we would use inverse cosine instead of regular cosine. So I want to kind of explain exactly why it is that inverse cosine works in this situation. And this next part is going to be like a little bit technical, but then we'll get back into some examples. So I just want to kind of point out, I guess, the way that using inverse trig in triangles is a little bit different from using it when we're on the unit circle. So when we're on the unit circle, or like just in general for any angle theta. So in general, if theta is just any angle, or kind of can be any angle. It is not necessarily true that let me say it this way, that if cosine of theta is equal to, let's say, a over b, then inverse cosine of a over b is equal to theta. And I'm just choosing cosine just to pick one of them, but I could have said this with the other trig functions. So what do I mean by this? Well, what I mean is that there are examples of angles such that if you take cosine of the angle and get a number, and then you take inverse cosine of that number, you don't actually get the same angle, right? So for example, let's say that your angle was, I'm going to go back to radians since I'm drawing this on the unit circle. Let's say if your angle was 7 pi over 4. So if theta is equal to 7 pi over 4, so where is that angle? I think the easiest way to think about it is that it's very close to being 2 pi, right? Because 2 pi would be 8 pi over 4, and this is 7 pi over 4. So that means that it's pi over 4 away from 2 pi, which means it's here. So the coordinates of this point are root 2 over 2 and negative root 2 over 2. So what is cosine of this angle, 7 pi over 4? Well, it's that x coordinate, which is root 2 over 2. However, what happens if we take inverse cosine of root 2 over 2? Well, inverse cosine doesn't deal with angles that are in quadrant 4, right? Inverse cosine is only looking for angles that are between 0 and pi. So inverse cosine, maybe let me change the color just so that this picture makes a little bit more sense. Oops, whoa. Oh my gosh. Okay, I'm just going to change that color. So inverse cosine of root 2 over 2 would be equal to pi over 4, right? Because that's the angle that also has an x coordinate of root 2 over 2, but it's also in the right part of the unit circle. Because when we're talking about inverse cosine, we're looking for angles that are in that part of the unit circle. So we just kind of came up with an example where when you take cosine of the angle, you get a particular number, but when you take inverse cosine of that number, you don't get the same angle that you started with. So that's kind of the way it is in general. However, if you know what quadrant you're dealing with, then you can say something like that. So, and let me just write down one other thing here, which is that basically the same is true for sine and tangent. I'm just, I just chose to use cosine as an example. So basically, if we had placed a restriction and we had said, instead of saying theta could be any angle, if we said if theta is an angle between 0 and pi. So if we started with an angle between 0 and pi, it would be true that you would get like the same thing by doing, cosine of the angle and then taking inverse cosine. Because like in this picture, let's say that we had started with the angle pi over 4. So then you would have gotten pi over 4 back, right? It would, cosine of pi over 4 is root 2 over 2, and inverse cosine of pi of root 2 over 2 is pi over 4. So if you're in the right part of the unit circle, you do have this kind of back and forth perfect correspondence. And so the nice thing about angles in right triangles is that angles in right triangles are between 0 and 90, right? You can't have an angle in a right triangle that is bigger than 90 or that is smaller than 0. Just doesn't work. It wouldn't make a triangle. And so because of the way that the unit circle angles line up, so the part that I already highlighted here was the part of the unit circle where, and maybe let me write it down here, or I'll draw another picture down here. I think I have to copy and paste this. Okay, so we know that this is the part of the unit circle where when you use inverse cosine, you get like your answer comes out to be an angle in that part of the unit circle. When you're working with inverse sine, it gives you an angle between negative pi over 2 and pi over 2. And then when you're doing inverse tangent, it also gives you an angle between negative pi over 2 and pi over 2. And so if you notice, what do all of those have in common? They all have in common quadrant 1, right? If you have an angle that is in this part of the unit circle, it's gonna, like, inverse cosine, inverse tangent, and inverse sine all can give you that angle back when you take the inverse. So if you have an angle theta that is between 0 and pi over 2, it is true that if cosine of theta is equal to a over b, then taking inverse cosine of a over b is definitely going to give you back that same angle theta. And then same thing if you take sine of an angle and you get a particular number, and then you take inverse cosine, or sorry, inverse sine of that number, you'll get back the same exact angle you started with. And then same thing with tangent. So if you know for sure that tangent of an angle is a particular number, and it doesn't have to be a fraction. I'm just writing it that way because oftentimes they come out to be, but I could have said a different number like n or something like that. Then inverse tangent of that same number is also going to be theta. So basically what I'm saying is that if you have an angle that is between 0 and 90, things just kind of work out nicely. Like, you don't have to worry about the angle that you started with not matching up with the angle that you get by using inverse trig. So what does this tell us when we're dealing with right triangles? Well, because angles in right triangles are always going to be between 0 and 90 degrees. Basically, it tells us that inverse trig just kind of works nicely. It's going to give you the angle you're looking for. It's not going to give you some other random angle that, or not random, but it's not going to give you some other angle that wasn't the angle that you're actually looking for. So what we can say in general is that if you have a right triangle, let me change color. I feel like I want to make this next part stand out a little bit more. What color should I use? I wish I had a live audience so you could give me your request. Let's do purple. So if you have a right triangle, and you have an angle theta, and you call this your opposite side, this your adjacent side, and this your hypotenuse, it's always going to be true that if you take inverse sine of the opposite side over the hypotenuse, you're going to get your angle theta. And if you take inverse cosine of the adjacent side over the hypotenuse, you're going to get your angle theta. And if you take inverse tangent of the opposite side over the adjacent side, you're going to get your angle theta. So basically, what am I saying now? I'm basically justifying what we did in that first example. So first example, we used inverse trig, and now I'm telling you why it is that you can use it. You can use it because you are guaranteed to get the right angle back, because your angle is in the right part of the unit circle, or it's in like the right range of angles that we know that inverse sine, cosine, and tangent are all going to give you the right kind of answer. Okay, so let's do some examples. We're going to do a couple more that are just like, or one more that's just like a picture of a triangle, and then we'll do a couple that are word problems. So let's say that we have a triangle here. So very long and skinny triangle. Well, that one came out pretty good. So let's say that we know that this side is length 10 and we know that this side is length 50, and we're trying to figure out what is this angle here. So if you think about it, basically what I would recommend doing on these questions is look at the information you have and what you're looking for and figure out what can relate that information. So the information we have is this side, and then we're looking for this angle. And so the relationship amongst those is that it's the opposite and the adjacent side. So because we know the opposite and the adjacent side, that tells us that we should use inverse tangent. So you don't have to write down this first step, but I think sometimes it's nice to first kind of write things down in terms of regular trig. So tangent of this angle would be 10 over 50, right? Opposite over adjacent. And that reduces to 1 over 5. And so what does that tell us? Well, if we're trying to actually find theta, we can do inverse tangent of 1/5, and that will give us our angle theta. And so if you type that into a calculator and make sure your calculator is in degrees mode, you'll find that it's approximately equal to, and I guess for some reason my notes, now I started doing only 1 decimal place. So I guess that's what we'll do the rest of this video, is 1 decimal place. So it's approximately equal to 11.3 degrees. So whether you're going to use inverse tangent, inverse cosine, or inverse sine just really depends on what information is given and which angle you're looking for. And I would really not recommend, if you really wanted to, you could use the Pythagorean theorem and find what this side is, and then you could use a different trig function. But the problem is that when you use the Pythagorean theorem, you'll probably end up rounding, and then that's just going to throw your answers off. So it's better to work with what you're given than to have to force it to be a different trig function. All right, so let's do an example that is going to be a word problem. So a 40-foot ladder is leaning against a building and it is its base, it's 6 feet away from the bottom of the building. And so the question we're going to answer is, what is the angle between the top of the ladder and the building? Okay, so let's draw a picture and see what's going on here. So we have our building. So I'll just put some windows on this so we know it's a building. Okay, so here's our building. And then we have a ladder that is leaning against the building. And so we know that this ladder has a length of 40 feet. And then we also know that the distance between the bottom of the ladder and the building, we know that that is 6 feet. And then the angle we're trying to find is this angle, the angle that is between the building and the ladder. And so in this case, if we look at what sides we have the opposite side and the hypotenuse. And so that tells us that we want to use inverse sine. And so we can start by writing down sine of theta is going to be equal to 6 over 40. And you don't have to reduce this, but it's you might as well. So what does 6 over 40 reduce to? Well, they're both divisible by 2. So we can rewrite this as 3 over 20. And so that tells us that to find theta, we can do inverse sine of 3 over 20. And if you type that into a calculator, that is approximately equal to 8.6 degrees. All right, so one more example. And this one is going to be with an angle of depression, because I think those ones are sometimes a little bit trickier to kind of visualize what's going on. So let's say that we have a boat is on the water, and it's a distance of 1,200 feet from the base of a lighthouse. And specifically, the lighthouse is, let me actually write it this way. The lighthouse is 200 feet tall. And so the question is to find the angle of depression from the top of the lighthouse to the boat. Okay, so we have some water here, and we have our lighthouse, which I'm not even going to try. I'm just going to go like this because I don't, well, I'll make it a little better than that. Okay, so here's our lighthouse, and we know that this is 200 feet tall. And then we have a boat out on the water somewhere. And we know that the distance, the horizontal distance between them is 1,200 feet. So the angle of depression, if you remember, is basically if you go kind of horizontally straight across from the higher point in your picture, and then you measure the angle that goes down, and that's why it's called the angle of depression. To depress something is to kind of make it go down. And so we're looking at this angle here is what we're looking for. And actually, and you don't need to know this, but if you know your geometry, it's actually the same as this angle because these two, this line and this line are parallel, but you don't have to worry about that. So what's our triangle? Well, we need to kind of redraw a couple of things. So you could actually draw theta where I just had it in green, but if you didn't realize those two angles were the same, your triangle would be this one. So I'm going to go back to my pink. I like that pink color. So your triangle is this one, where we have that angle theta, and then we know that this length is 200, right, because of symmetry, and we know that this side is also 1,200 because of symmetry. So to solve this, we look at what information we have. So we have the opposite and the adjacent side. So we know that tangent of theta is equal to 200 over 1,200. And that reduces to, let's see, 1 over 6. And so that tells us that if we take inverse tangent, or maybe let me say it this way, that means that theta is going to be equal to inverse tangent of 1 over 6. And so if you type that into a calculator, you'll get approximately 9.46, or I guess let's round it to 1, 9.5 degrees. And by the way, if you've taken like science classes where you talk about significant figures, you might have noticed that we're not really being very consistent with that stuff in this class. And I just really, we don't really have the time to get into stuff like that. So I don't care so much how many decimal places you round to. I will usually tell you in the question what I expect, whether you should round it to 1 or 2 or the nearest whole number or whatever. And then same thing on the online homework. Sometimes the question is coded a certain way and it will always kind of tell you what to expect. If it's not specified and it's a question where you have to use your calculator, I would recommend putting like 3 decimal places, maybe even 4, just to be safe. Okay, so one more thing I want to do, which is a little bit different, is I just want to quickly show you how you could do a question similar to things that we were doing in yesterday's video, but just a slightly different way. So basically, this is another approach to evaluating something like sine of inverse cosine of 1 over 4. So the way that we did this in yesterday's video is we went on the unit circle and we found an angle where the x coordinate was equal to 1/4. But what we could do instead is we could try to draw a right triangle. And so I want to be careful that really the only reason that we can do that in this case is because 1/4 is positive. If we had a negative number there, then it wouldn't really make sense to draw a right triangle. Then you would want to go on the unit circle because that would mean that you have basically an angle that would not be an angle that actually lies within a triangle. Because triangles don't have negative side lengths, right? That just doesn't really make sense. And so what we're going to do is we're going to try to figure out, how can we draw a triangle that would give us cosine equal to 1/4. And then once we have that triangle, we can use that triangle to find sine. And so the reason I'm bringing this up is basically that next week we'll get into some examples that are kind of along these lines. And this is kind of like a stepping stone on the way to those slightly trickier examples. So we're going to start by focusing on this. So we're going to think about inverse cosine of 1/4. We're going to think of that as being an angle. And it's going to be an angle in a right triangle. So if inverse cosine of 1/4 is equal to theta, that means that cosine of theta is equal to 1/4. And the reason that we can make this flip is because we're in a right triangle, we know that it's an angle that that kind of is in the right part of the unit circle. And it's basically because the 1/4 is positive, because we started with a positive number. So if cosine of theta is 1/4, what's that going to look like in a triangle? That means that the adjacent side should be 1 and the hypotenuse should be 4. And so we can just draw a picture. It doesn't need to be perfect, right? We're basically just using this as kind of a placeholder as we try to figure out some stuff. So if this is our angle theta, that means that the adjacent side is 1 and the hypotenuse is 4. And so we need to figure out what this vertical side is. So maybe we can call it y. So let's find that other side. How do we find it? We can use the Pythagorean theorem. So kind of like how in the other video, or in the other example, the one we did at the beginning, we used the unit circle equation to find the missing information. This time we're using the Pythagorean theorem, but the unit circle equation and the Pythagorean theorem are actually very closely related. So we're basically doing the same thing, just with a different viewpoint. So how do we find y? We would say 1 squared plus y squared is equal to 4 squared. And so that tells us that 1 plus y squared is equal to 16. And so that tells us that y squared is equal to 15. And y is going to be equal to square root of 15. We don't have to do plus or minus because we're dealing with a triangle. It's just not going to be a negative side. So now that we know that this side is equal to square root of 15, now we can go back in and say, okay, sine of theta. So, going back to what are we actually trying to do here? We're trying to find sine of inverse cosine of 1/4. So inverse cosine of 1/4 is theta, right? It's this angle theta. And so now to find sine of theta, well, now that we have a nice picture, we can just do opposite over hypotenuse. So that's going to be square root of 15 over 4. So we'll come back to this idea a little bit more next week, but I just wanted to kind of give you a preview so you can start thinking about how you can also use right triangles to kind of figure out different things about inverse trig functions.